We have seen that we can use linear programming as a technology to solve a number of problems. And formally, this involves what we call a reduction. So rather than reducing to linear programs, let's look at how we can actually reduce to network flows, which we saw already could be reduced to linear programs. So here is a problem which seems to have nothing to do with flow. So we have some course allocation to be done in a school. We have a collection of teachers and we have a collection of courses. And each teacher has indicated a preference of which courses he or she is willing to teach. So here we have 4 teachers, Abbas, Chitra, Madan and Sunita. And we have 4 courses, math, history, biology and economics. So Abbas for instance is willing to teach history and biology. So that's these 2 edges. So this indicates that Abbas is okay with teaching these courses. Similarly, for instance, if you look at Madan, Madan is happy to teach history or economics. Okay. So each teacher has indicated a collection of courses that he or she is willing to teach. Now what we have to do is allocate these courses to the teachers. Obviously, each course is going to be taught by exactly one teacher. Okay? But also we would like that each teacher teaches only one course, and that course should be something that the teacher is willing to teach. So we would not like an allocation, for example, which asks Abbas to teach math because he has indicated that he is not comfortable teaching math. Okay? So we want to find such an allocation that each course is taught by a single instructor. Each instructor teaches only one course, and that is a course which he or she is willing to teach. So this is what is called a matching problem. Okay? In particular, it's called bipartite matching. So what is a bipartite graph? A bipartite graph is one in which the vertices come in 2 groups, which we call V0 and V1. And all the edges go from V0 to V1. So there are no edges inside V0, there are no edges inside V1. Okay? So this is the example here. So this, for example, the teachers are V0 and the courses are V1. Now there are no edges between courses, there are no edges between teachers. All the edges are from a teacher to a course. Okay? Now what we have asked is to find an allocation. What will an allocation do? An allocation will pick an edge and say, for instance, that Abbas will teach history. Now once Abbas has been assigned history, then this means that this edge cannot be taken anymore, because Abbas cannot be assigned anything else. It also means that this edge cannot be taken, nobody else can be assigned this edge cannot be taken. Okay? So we want to find edges such that no 2 of them share an endpoint. In this example, if 2 of them share an endpoint on the left, it means that the same teacher is being asked to teach 2 courses. If the 2 edges share an endpoint on the right, it means that the same course is being taught by 2 different teachers, neither of which we want. So we want a matching. We want a matching which is a subset of edges so that no 2 of them share an endpoint. And in particular, if we have an equal number of nodes on each side in a bipartite graph, then we can expect or hope that everything on the left is matched to something on the right. Okay? If we don't have an equal number, of course something has to be left out, because each edge will match up 2 people. So supposing we have 5 teachers and 4 courses, then 1 teacher will not teach a course. Or if we have 4 teachers and 5 courses, then some course will not be taught unless a teacher takes 2 courses. But if you have 4 teachers and 4 courses, you could ask whether there is a way of matching them up so that every teacher teaches a course and every course is taught by a teacher. This is what is called a perfect matching. So what has this got to do with network flows? So here is how we can answer this question using network flows. We add a spurious source node feeding into the teachers, and we add a spurious target node, a sink node coming out of the courses. So implicitly all our edges are now going from left to right. Right? So we have the direction. So we are trying to flow something from left to right. Now what we want is to assign capacity 1 to everything. So every edge in this has capacity 1. Right? So supposing we find a maximum flow. So a maximum flow will select some subset of these teachers. Right? Hopefully all of them. Because it is a flow, that flow will go into a teacher and out of a teacher, so it will select one of these edges, say this one. Okay? And therefore, now it will flow from this out here. Now because the output can only take 1, I can only flow 1 from history to the sink, it cannot allow another thing to come in from here. Okay? So if I had a flow 1 here and a flow 1 here, then 2 would have to flow out of the history, but I've got it. So we're putting a flow capacity of 1 on all the edges, I ensure that exactly one teacher and one course can be selected in the matching. And now if we maximize this flow, it maximizes the number of teachers who are connected to the courses, and therefore it maximizes the matching. Right? So we have managed to take a problem involving something very different involving graphs and model it using network flows. So this is a general example of what we call a reduction. So we want to solve a given problem, problem A, but we don't know how to solve it. But we do know how to solve another problem B. Right? So in our case, this is matching, and this is flow. So what we do is we transform our problem from matching to flow. So we take our matching problem and then we add a source, we add a sink, we add capacities, convert it into a flow problem. Right? So having converted it into a flow problem, we solve it. So this is the diagram shown below. Right? We have an algorithm for B. So now we have a matching input. We convert it into a flow input. This is the flow solution that comes out. Okay. And now we look at the flow solution. Wherever we see a 1, that is our matching. Wherever we see a 0, that's not in our matching. So from that we get a matching solution. Right? So we can invert the solution from the inner problem to get a solution to the outer problem. So this is a reduction. Okay. So we say that A reduces to B. To solve A, I can convert it to B and solve B instead. Okay. And therefore if I have an efficient solution for B, and if this conversion process is efficient, the process of setting up the problem for B and interpreting the answer are both efficient, then that's the efficiency of the algorithm for B composed with the efficiency of the pre-processing and the post-processing step will give us an efficient algorithm for A. Right? So without directly attacking A, I have indirectly found an efficient algorithm for A by exploiting the existence of an algorithm for B. So as we said before, our example that we did in this lecture says that bipartite matching in this way reduces to max flow. Now what we saw last time was that max flow itself reduces to linear programming. But the key is that the pre-processing and the post-processing must be efficient. When we went from max flow to linear programming, what we did was we introduced one variable FE for each edge E. Okay. So therefore, that is an efficient translation because it produces a linear program whose size is comparable to the input graph for max flow. Earlier we had seen an example of network bandwidth where we produced a linear program which required one variable per path in the network. That would not be an efficient reduction because that would require an exponential amount of work to construct the linear program and to reinterpret. Okay? So therefore we have to be careful in order to, if we are only interested in solving the problem, is one thing to convert it to another problem, but if we want to exploit the efficiency aspect, then the translation to and from the inner problem must also be efficient. So we will see that another interpretation of reduction is also useful for us. So what we have seen that is that if A reduces to B, okay, then if B is efficient, then this implies that A is also efficient, because I can use the solution for B as solution for A. But supposing I have that this is not efficient or not known to be efficient, if I have some reason to suspect that there is no efficient way to do A, then if I can show that A can be reduced to B, then this also means that B cannot be efficient, because if it could be done efficiently, we know that we can do A efficiently, but we have reason to believe that A cannot be done efficiently. Right? So reduction can be used depending on the way in which we exploit it, either to transfer a positive result from B to A or a negative result from A to B. That is, A is not known to be efficient, B also is not known to be efficient. So in this last couple of lectures, what we have seen are two what I would call big hammers. Okay, so we have linear programming and network flows. We actually express network flows in terms of linear programs, but network flows independently are a very powerful modeling formalism. So many algorithmic problems can actually be reduced to one of these two. Either you can set up variables and set up a linear program, or you can take a graph theoretic problem and model it using flows. And the nice thing about this is that linear programming and network flows are both very standard problems for which people have invested a lot of time to write general purpose tools which solve these problems. So you can set up an arbitrary linear program, an arbitrary network flow, give it to the tool will give you an answer. So you have efficient off-the-shelf implementations. So in many practical situations, rather than try and solve an algorithmic problem directly, it does often make sense to think of whether it can be modeled as a linear program or a network flow, and then use an off-the-shelf package to solve it. But of course, you have to be able to express the problem in terms of one of these things. So in order to understand whether you can do so or not, you need to spend some time analyzing what can and cannot be expressed as linear programs. In linear programs, the crucial thing is that the constraints must be linear functions. Sometimes you have constraints which refer to the product of two variables. This is not a linear function. Similarly, in network flows, you have to make sure that you can actually model it as a source to target flow. Okay? It cannot be something going around and around in a network. So within these constraints, however, both of these are extremely useful generic problems for which efficient solutions do exist and which can be exploited in a large number of situations to solve the given problem at hand.